Hello, I'm
Hello.
Ray Bueland. I'm a research scientist. I spent about 30 years out at the National Earthquake Center in Golden.
Can you speak a little louder?
I can try. Can we close the door? That'll help too.
As soon as you started, I started doing that PDT.
So I'm Ray Bueland. I'm a research scientist. I worked for about 30 years out at the National Earthquake Center in Golden. So I'm an earthquake guy, seismologist, with a background in geophysics. And retired from there at the end of 2010 as a senior scientist. And now I do lectures like this on cruise ships. So this is a very different venue for me. I'm a lot closer to you guys, so, you know, lots of possibilities for interaction.
The deck isn't moving all over the place.
Yes,
Wait a
yes.
minute, it is moving. What is it?
This is my lovely assistant for my talks on the cruise ship.
Well, I mean, it's rotation of the earth.
There you go, yeah. So, one of the reasons that I like doing these talks at Mile High Con is I do like the hard science talks, and so I thought I would contribute. And the reason I'm doing ice ages is they're incredibly interesting, and of course they also make a great basis for fiction. So I thought that getting a little real science into the fictional ice age fantasies would be good. And the other reason is that there's a lot of progress been made on understanding ice ages. These are things that have been known since the mid-1700s, but until very recently, it was really not understood how they worked. And so that's what I want to go through, is how they really happen, how they really work, and what the effects are. So I want to start out with the current glacial cycle, and you'll see in a minute why we call it a glacial cycle instead of an ice age. So what was it like? Well, it turns out that a large part of the northern hemisphere was completely frozen. It was under 3 kilometers of ice, 2 miles of ice. So here's a polar view of it. That area in blue is where this ice cap was. So you can see it covered about half of North America and a good part of Siberia as well. And what's left of that ice cap now is the ice sheet on Greenland. So this is an XKCD webcomic. He did a nice job of showing the skyline of various cities relative to the thickness of the ice at the time. I particularly like Toronto. 2 kilometers of ice makes the CN Tower look pretty small. So there was so much ice that the weight of the ice actually started forcing the continents down. It actually made them sink. And we know that because we can see them popping back up today. So these blue places are places that the continents are actually rising at something like a centimeter per year, so a little under half an inch per year. And it's been doing this for the last 10,000 years. Now, curiously, we actually have a little bit of sinking around the edge where we have this uplift. And I'm going to get to why that makes sense in just a minute. So if you had all that ice, and now you don't have all that ice, where did it go? Well, it melted and it ran into the oceans. And so what this is showing is the rise of the sea level. The ice age, people argue about where it ended, but kind of the depths of the glass glacial period was around 20,000 years ago. And the sea level started rising as the ice started melting. And about 8,000 years ago, it stabilized more or less where it is now. Notice, though, in the middle, there's all of this kind of weird lumps and bumps. It wasn't a smooth process. It didn't just start melting and the sea level started steadily rising. There's these sudden bursts where it rose rapidly for a while and then it flattens out a little bit. And we'll get to what that means in a minute, those meltwater pulses. So I'm foreshadowing a lot here, right? There's a lot of things coming. But I did want to get to the point that this actually takes a long time, not long geologically, but long in terms of a human time frame. So on the left here, we have the current warm period. That's where we are now. And it's nice and toasty. We're very well adapted to it. It's I'd hate to see it get a lot colder. But the current warm period lasted 10,000 years. The glacial period before that lasted 90,000 years. So there's a lot more cold than there is warm. And I think one of the things you can see, well, is that, well, we'll talk about this in a second. Getting ahead of myself. The interesting thing is that it's really not that big a temperature difference in terms of the global average temperature. It's only about 8 degrees centigrade or about 14 degrees Fahrenheit. But that's the temperature over the entire Earth, okay? So our weather and stuff is on top of that, and it turns out this very small amount of temperature change applied over the whole Earth for these thousands of years is enough to completely change everything with all the ice sheets and woolly mammoths and all the rest of this stuff. Now, it's kind of interesting that that part circled there is the peak of the last warm period. And it's actually a lot higher than the current temperature is now. It actually, things conspired so the temperature got quite a bit hotter, at least in the northern hemisphere, particularly Europe, than it is right now. It was so warm that there were actually hippopotamuses in the Rhine River. Okay? It's kind of cool. All these lumps and bumps in the glacial period are kind of interesting. People are still arguing about what caused those, but they appear to be real. During this long glacial period, it's not uniformly cold and then uniformly warm. It actually varied a lot. And those variations are kind of important in human history, as we'll see in a little bit. The fact that it sometimes was a little bit warmer, then a little bit colder, and so forth. Well, it turns out there wasn't one of these glacial periods. There's a whole bunch of them. So there's the current one right there. The present is on the left. But there's another one very much like it. And another one before that. And another one before that. Kind of every 100,000 years you have 90,000 years of cold and 10,000 years of warm. So it's kind of spooky because it's been about 10,000 years of warm right now. Not sure what that means, but there's a whole series of these things that we perceive as ice ages, but which geologists call glacial.
Is there are there periods when the Earth doesn't do glaciations? So we're seeing this not quite periodic but repeated thing.
Yeah, we're going to get there, I think, very, very soon.
Okay.
But you're right, you're on the right track. There are periods when we're not in what the geologists term an ice age, and there were ice ages that they don't know that they were necessarily periodic like that. So this is kind of, we know more about this one than we know about older ones, but this may be very different than older ones. Well, I want to get into the meltwater pulses because they're incredibly cool. The ice sheet was up in that area that's circled, and this area here is Lake Agassiz. This doesn't exist anymore. This is up in northern Canada. This was a lake that formed from the melting ice sheet, and it couldn't escape. It was trapped because the rivers in northern Canada were north. Okay, so the ice sheet's actually blocking its exit into the Arctic Ocean. At its peak, it's thought that it had as much fresh water in it as all of the lakes on Earth today combined. Okay, this was a big feature. At this particular time, it had merged with Lake Ojibway, which is much shallower, so it's, even though it's a bigger lake in aerial extent, it actually has less water in it. Eventually, it broke free, did an end run around the ice sheet into the Arctic Ocean. And what's happening is you're taking this huge volume of water and you're dumping it into the ocean, this huge volume of fresh water, raising the sea level, but fresh water is a lot lighter than the seawater. And so you're disrupting currents, and what typically happens after this is there's a period where the temperature kind of stabilizes again. It quits warming. And so you get this funny pattern of sea level rising suddenly and flattening out because it actually got colder again. And then it starts warming and building up these lakes again, and then you have another event. So it looks like there were many of these things. Here's another example. This is now farther south. This is Pacific Northwest. You can see the ice sheet was up there. And when the ice sheet was farther south, it actually dammed up this very, very large lake called Lake Bonneville. All that's really left of it now is the Great Salt Lake. There's another one over here, kind of on the California-Nevada border. And again, they kind of did an end run. As the ice melted, that water eventually ran through the Snake River Valley and the Columbia River and out to the ocean. When you
Shouldn't there
have
be a
that
lake in
much
Idaho?
water.
Wasn't there one in Idaho?
Yeah, they were all over the place. These are just some of the bigger ones that people have heard of. In fact, this is drainage from the one in Montana. They're really literally all over the place. This is something called the Shonkin Sag. Geologists thought this was a sag feature. It actually was, when it emptied one of those very large lakes, it carved this very shallow valley. And it's a little hard to see, but right in here, there's a pretty good-sized factory or mining operation or something. This is a very, very large feature. Okay, that's a lot of water flooding down here. Well, a lot of weird things happen with this rising sea level, this melting water, and so forth. One of the intriguing ones is that the Baltic appears to have melted actually earlier than some of the other areas. And there was actually a freshwater lake dammed by the ice to keep it from escaping into the North Sea. This was maybe between 10 and 12,000 years ago. So just as the melting begins, they actually have this huge freshwater lake in the southern Baltic Sea. And eventually it escaped where that red arrow is, past Denmark out into the North Sea as the ice melted. Persian Gulf's another example. This is a case where you've got a shallow sea. There's a sill at the entrance, so it's actually shallower between the sea and the Indian Ocean. And so as the sea level dropped during the Ice Age, that all evaporated. That was just dry land. And eventually, as the sea level rose, the salt water then began coming in and filling up this basin. So you got this big flood scenario. They think a very similar thing happened in the Black Sea. Again, as the sea level dropped, it sealed it off, all that water evaporated. As things warmed, the fresh water, the meltwater began running into it, filling it up again. But eventually the Mediterranean got high enough, it went over that sill. And they can see on the bottom something that looks like there was a very large waterfall there at one time, and maybe several times.
They found log cabins preserved.
Yes, they have. Well, they found Neolithic dwellings on the bottom of the ocean. Yeah, because those people lived at the shore, and it's not the shore anymore, right? So let's talk about what geologists consider an ice age. It's really a little different than what I always considered an ice age, the last glacial period. But there's been many of these things. And so here's a picture of the last 5.5 million years. And fortunately, time so far is still running the right direction. From right to left. It'll flip on you, so you gotta be careful. But you can see a couple of features here that geologists call the last 2.5 to 3 million years a single ice age that has these funny oscillations in it. And you can see the average temperature kind of dropped there for about 1.5 million years, and then it kind of flattened out. But at the same time, the variations between the warm period and the cold period are getting bigger and bigger. So is that going to continue going on? I don't know. But it suggests that the warm periods are getting warmer and the cold periods are getting colder. So this is what we call geologically an ice age. And what I want to do is put that into context. So now we're going to back off and look at 65 million years. Okay? That green line is showing you what the temperature was. You may notice there's 2 temperature scales there. And a long cooling trend. Okay, from 50 million years ago, it's just generally been getting colder and colder until the present. But lots of little interesting features there, and we want to kind of look at what may have caused those. Now, you notice there is two temperature scales. There's one down here, and then another one they've sort of stitched together up there. And that has to do with the way they measure temperature millions and millions of years ago. There's a lot of interesting features in there that they think are related to Antarctica forming ice sheets, having the ice sheets melt, forming again, and so forth. So how do we make a picture? How do they go out and measure temperature 50 million years ago? And it turns out they use oxygen atoms. It turns out that oxygen atoms, like most other atoms, come in flavors, okay? If we add a couple of neutrons, it doesn't change it. It's still oxygen, but now it's a little bit heavier, okay? Still has the same 8 protons and 8 electrons, but it's got 2 more neutrons. And it turns out that the living creatures are sensitive to this. And so there are little sea creatures that actually take in more of the heavy variety when it's colder. And so you can use this to make a thermometer that works in the distant past. The typical creatures they use are these little guys. They're little shell creatures called forams. Geologists have been studying these forever and ever. That little scale there is 500 microns. Okay, these things are like a 64th of an inch across. They're very, very tiny. But they're very useful because their shells preserve this ratio between lighter oxygen, heavier oxygen, and you can use it to tell what the temperature is. So what caused the cooling trend? I'm going to go through 3 different things, and it's not 3 different possibilities. It's thought that these were different things that acted to help cool the Earth at different times in this 50 million year decline. So it all goes back to plate tectonics, which is really good because I'm a seismic guy and plate tectonics is key for earthquakes. So 70 million years ago, the Earth looked something like this. And what you see is the Arctic Ocean almost isn't there. It's completely landlocked, very shallow, not much at all. The other actor that's going to be important is India. The Indian subcontinent is zipping towards a rendezvous with Asia. It's eventually going to crash into Asia and create the Tibetan Plateau by uplifting it. Now notice that it doesn't look like India. It's got this big chunk at the top there. That's all gone now. That's underneath Asia. Okay? This is a pretty dramatic geologic event when it hits, and it turns out it has consequences for climate. Well, the other thing we want to look at is Central America. You can see it there on the picture, but it's all grayed out. What's really going on there is we have active tectonic processes. We've got plate tectonics going on there, but it was actually not land. Okay, there was no land blocking the ocean circulation between the Atlantic and the Pacific. So the currents going around the Atlantic could actually go right through into the Pacific.
What is that land way to the west there?
Over in here.
Yeah.
Yeah, there's a lot of little continental fragments that eventually are going to get aggregated onto other bits and pieces. So we're going to animate that a little bit. 50 million years ago, which if you remember was when the decline started, the Arctic is a little bit bigger. India is getting a lot closer to Asia. And we still have our ocean current zipping through there. It's still not closed off. So we're going to move it forward a little bit more. Now India has crashed into Asia there. There we go. It's crashed into Asia there, and that part in yellow is double thick crust. It's actually come in so hard and so fast. The Tibetan Plateau is twice as thick as, say, North America or South America. And it's got this tremendously high elevation, and that turns out that's going to be important. The other thing going on is that the Central America still isn't closed at 10 million years ago. It actually finally closed off those currents about 3 million years ago. 3 million years is when our current ice age actually began, right? So coincidence? Maybe. So I'm going to start out with a little fern called a Azolla. Azolla is a little freshwater fern, very tiny. And it turns out that we know there was a lot of it living in the Arctic Ocean about 50 million years ago. We know this because we can see the fossils. This stuff died and sank to the bottom and created huge beds of coal and oil. Well, it turns out the Arctic is very shallow at that time. This is almost all continental shelf. There's no deep water. And that turns out to be important for the story. But it's also very isolated. It's still pretty landlocked at 50 million years. And because it's landlocked, they think it might have been stratified. So what that means is we've got all these huge rivers in Asia and in North America running north, dumping fresh water in. But this sea is actually not mixing, okay? It doesn't have currents from outside. And so the fresh water is sitting on top and the salt water is sitting underneath. Well, these rivers are also bringing a lot of nutrients in. They're eroding stuff from the surrounding land, and they're dumping a lot of things that might feed a freshwater fern. And you got all this fresh water. During the summer, you got 24 hours of sunlight. It's really an ideal environment for growing these little ferns, and they went completely bananas, okay? And so during the summer, it's thought that they could have doubled their biomass every 2 to 3 days. This went on for 800,000 years. Now, it's no wonder there's a lot of hydrocarbons in the Arctic today, and we know it's from Azolla because you can see the fossils. So what happens when you have these things living and dying like this? Well, normally they would suck up carbon dioxide, they would die, they would sink to the bottom, they would decay and release that carbon dioxide. But here we have this stratified ocean where things aren't moving, okay? And so they sink to the bottom. Well, the first ones, they decayed and they sucked up all the oxygen in the water, but after that, they couldn't decay anymore. No oxygen, it's anoxic. And because of that, these things, instead of decaying, they took all of that carbon dioxide with them. They sucked it out of the atmosphere, brought it to the bottom of the Arctic Ocean, and it stayed there. And so this is the beginning of this decline in temperature. Well, I want to move on to India and the Himalayas, highest place on Earth. It's still rising, actually, at about 1 centimeter per year, a little under half an inch. And it's exposing all this lovely fresh rock, and it has the fastest erosion rate on Earth. In fact, they think that something about a quarter of all the erosion on Earth happens in the Himalayas. And here's an example of it. We were actually in Tibet 2 weeks ago, and you have this nice erosional feature dumping into the Brahmaputra River. There's a little bridge over here. That's a railway bridge for scale. I mean, this thing is huge. And that's typical all over the Tibetan Plateau, and it's worse even on the southern side of the Himalayas where you've got all this water. Well, the point of that is that weathering actually also pulls carbon dioxide out of the atmosphere. What happens is that as you expose fresh rock, it begins to interact with the atmosphere. The carbon dioxide interacts with the chemicals that are holding the little grains together, and the rock starts falling apart, and you get all this erosion. Well, those chemicals now with that carbon dioxide run down the rivers, they run into the ocean, they eventually form limestone and so forth. And it's thought that they actually get subducted. They get pulled down inside the earth through these plate tectonic processes. And so again, we're getting rid of carbon dioxide, this greenhouse gas in the atmosphere that's tending to make everything cooler. Well, Panama finally forms somewhere between 3 and 5 million years ago, and it blocks those currents. And you can see how contorted it is. The currents in the Atlantic are noodling into the Caribbean, and then they're noodling out again because they can't go across into the Pacific and vice versa. So we don't really know the exact effect that would have, but it is coincidental that this closing of the Central America coincides with the beginning of our current ice age. And we do know that disrupted currents can have a big effect on climate because they transport a lot of heat. So I'm going to put that all together for you. Here's our picture again. We start out with the Azola in this very, very steep decline. Okay, so it sucked all that carbon dioxide out, but after a while it stabilizes again. It takes quite a long time, but it eventually stabilizes, and then we get all of this stuff I talked about before that seems to be related to Antarctica. Well, somewhere in here it starts declining again, and that's coincident with India running into Asia, raising up the Tibetan Plateau, and beginning this weathering process that's actually pulling carbon dioxide out of the atmosphere. And then we have this steep decline that started about 3 million years ago that seems to be coincident with the Isthmus of Panama finally closing the gap between the Atlantic and Pacific Ocean. So we can see geologic things that look like they are related to this temperature back there, and that are somehow controlling when we have these very cold periods, these ice ages. And there's the ice age right there, our little fuzzy thing right in the crack in the wall. Planted that way. All right, so now we're going to get to why it oscillates. Maybe. Well, it starts with this guy named Milankovic. He's a Serbian engineer. He was a pretty interesting guy, actually. He was a mathematician, an astronomer, climatologist, geophysicist, professor, an author, and it seemed to me pretty much an all-around cool guy. And he's the one, a lot of people worked on this problem, but he finally put all the math and all the astronomy together to show how little wobbles in the orbit of the Earth could trigger ice ages. And that's important because when you see those periodicities, you know it's not geological. Geology doesn't do that. It's got to be driven by astronomy. And so he showed how that might happen. And he put together 3 different things. Well, he put together a lot of different things, actually. 3 of them appear to be important. Eccentricity is one. It's got a cycle time of about 100,000 years, kind of coincident with the ice ages. And basically what's going on is that the Earth's orbit is actually not round, it's elliptical. But the ellipticity changes with time. So sometimes when the ellipticity is higher, the Earth during the wintertime would actually be much farther from the sun. Well, farther from the sun, and it makes a small difference. During the summer, it would be closer to the sun and warmer. As the Earth's orbit got more round, that effect would go away, and this oscillates over a period of about 100,000 years. Second one's obliquity. It turns out we know the Earth's axis tilts at about 23.5 degrees, but it actually bounces like a top starting to fall over. It actually wobbles a little bit, and that turns out to be important. It's not very big, a couple of degrees, but still significant. And then the final one's precession. This seems like it should be important, but it doesn't show up in the climate record as much. But again, what's going on here is that the spin axis is actually precessing with this period of 22,000 years. And what that means is that when the Earth is farthest from the sun, it makes a difference which direction the axis is pointing, right? Which hemisphere is getting getting the coolest. So let's take a look at our 5 million years of climate change, and we see that obliquity signal about 41,000 years that went on for 1.5 million years early on in the ice age when the temperature was still declining. And we see the 100,000 year cycle due to eccentricity here for the last million years or so. So it does look like Milankovic was onto something. Now the problem is these signals are not very big. But you can see a correlation. So they have found some little creatures in the ocean that they can use as a clock, and as a clock as a thermometer, but they can actually measure the total amount of ice that existed on Earth. And so the black line is the change in the volume of ice each year. And the red line is this Milankovitch forcing. And what they're showing is that if you look at the forcing in high latitudes, particularly high northern latitudes, it correlates with the amount of ice. Okay, as you have the Milankovitch cycles such that they're getting less sunlight, you start to get more ice. You get more sunlight, you start to get less ice. So the big mystery and the thing that has been hanging around for a very, very long time, really many decades, is how this actually creates this cycle, because Milankovitch cycles don't really change the total amount of sunlight that's coming on Earth. They just kind of redistribute it, right, to higher latitudes or lower latitudes. And the clue as to how this all happens is coming from the current climate research. So really just in the last decade or so, they're beginning to understand that there's a lot of mechanisms that can amplify that very weak signal and actually make these big changes in our climate. Just as a trivial example, if the Earth starts cooling off, particularly at high latitudes, we start getting more ice built up. Ice reflects sunlight, so now we're getting less total sunlight to the surface of the Earth, and it gets even colder, so it amplifies that effect. So why the Arctic? Why not the Antarctic? Well, the Arctic is still a special place, just like it was 50 million years ago. It's opened up, it's changed, but it's still kind of a pressure cooker for climate change. It's landlocked pretty much. Some interaction with the currents, more so than 50 million years ago, but still pretty landlocked. It's still pretty shallow. These are all continental shelves. They were all touching 50 million years ago. Now there's some deep water. Shallow water is important because it makes it a lot easier to form sea ice. Sea ice, of course, reflects sunlight. It has an extreme climate because it's at the pole, of course, so it gets a lot of sunlight in the summer, no sunlight in the winter. And so you're able to take this very extreme climate and amplify all those effects in this little tiny microcosm, the sandbox, that eventually can leak out and change the climate of the entire Earth. So this is what's called Arctic amplification. All right, well, I want to shift gears here a little bit. It turns out ice ages are really important to us. They may not be important to you right now, but they are actually very important to us because human evolution really interlocks with the ice ages. So looking at a long timeline, now we're looking at, 400,000 years, and we're seeing the last 4 glacial cycles. Time's going this way in this one. That's important because it'll be going backwards in the next one. The earliest modern human fossils that they found in Africa date to about 200,000 years ago during the previous glacial period. But they didn't really get out of Africa until the current glacial period. Now, it's always kind of intrigued me because the timing is such that they chose to leave a warm place for a colder place in the coldest time. I mean, why would you do that? Why wouldn't you wait till it was nice and warm and then walk north? But they didn't do that. They began to migrate out of Africa in the middle of the last glacial period. But notice there's a lot of those little warm peaks, so they may have picked warmer times rather than colder times. Well, it turns out part of the reason is that across what's called the subtropics, across the Sahara Desert, across the Middle East, it's very, very dry. There's this huge barrier to migration. However, during the glacial periods, we have evidence from the fossils that it actually was lush and green. It actually got water and it greened up, and it was no longer a barrier to migration. So the answer to why they migrated out of Africa during the colder periods is that they could. There was no longer this barrier. So it's thought that humans really colonized all of Africa between 170 and 130,000 years ago. Between 70 and 60,000 years ago, they began migrating east into Asia. So actually going across the mouth of the Red Sea, following the seacoast through Arabian Peninsula and then on into India and Asia. Somewhat later, between 50 and 40,000 years ago, they began going up through the Middle East and into southern Europe, where we have lots and lots of fossil evidence. Well, on a shorter timeline, and now we've got the time running backwards here, there's the picture of temperature. And I've superimposed on it the picture of sea level. And so you can see temperature stabilized about 10,000 years ago, and humans started changing about 10,000 years ago. That rising sea level continued to change climates, which is also important to a lot of archaeological sites. So we have the Paleolithic, the upper part of the Stone Age, back in here to about 10,000 years ago. And then the Neolithic starts somewhere around 10, 12,000 years ago. And it's significantly different. People are starting to settle down, they're making pottery and so forth. Completely different kind of behavior than they had before, and it correlates perfectly with the stabilization of the temperature. People could tend to be more settled because the temperature was stable enough and warm enough to grow crops. Well, of course, the beat goes on, and we have the Bronze Age fading into the Iron Age, all during this period where it's warm enough to grow enough food to feed large populations. So the earliest known monolithic structure is this place called Göbekli Tepe, or more or less. This is in Turkey, southeastern Turkey. And those little stone keys there are the first monumental stone structures that are known anywhere in the world, and it dates right to the beginning of the stabilization of temperature. Another important site in Turkey is one of the earliest farming communities known, and it's not, it's maybe a few thousand years later, they're actually beginning to settle down and farm in the Middle East. So the ice ages really have a lot to do with shaping how human evolution went and how human migration went. And so we're going to get to the question that was posed earlier. Well, not a question, but the comment that there are structures actually on the bottom of the Black Sea. This is true everywhere. Sea level at its minimum was 120 meters lower than it is now, 400 feet. Okay? Virtually all of the continental shelves everywhere in the world were dry land during the coldest part of the Ice Age. And of course, the human populations at that time that wanted to live near the ocean would have had their camps on those ancient shores that are now all under 400 feet wide. So you can actually see this. If you go to Google Earth, it's very cool. You can actually see these river valleys on the bottom of the ocean. Now, currents don't carve things like this. These were carved by a river when this was dry land. And you can see another one there, another one up in here. Okay, so now I have a question for time. How much time have we got? Oh, I could watch.
15 minutes.
I think we've got time to do my last little section, which I think is kind of science fiction-y and fun. I want to get into Snowball Earth, other ice ages, particularly other ice ages that may have been deep enough to freeze the entire Earth solid. And it has to do with what's called the faint young sun paradox. So we have the current luminosity, that heavy blue line up there. We're looking at the Earth's age in billions of years, starting from zero when the Earth was formed. And it turns out that the sun actually was about 3/4 of the luminosity that it is now. Okay, which means there was a lot less sunlight and it was a lot colder on Earth back at the very beginning than it is now. It turns out it's increasing at something like 8% every billion years. So that's important. If we look at temperature, which they can kind of estimate from the solar output, What I have in the heavy blue line, it's not quite at 0 degrees centigrade because seawater freezes at a little bit lower temperature. That's the freezing point of seawater. And the prediction from the solar output is that the temperature should have been well below the temperature where seawater will freeze through this entire interval. The ocean should have been frozen solid. Okay? But we know it's not. That's why it's a paradox. The reason we know it's not is we have evidence of early single cell life in the oceans that are much earlier than the point where it should have thawed out. So what's going on, you know? Well, greenhouse gases are everywhere. And it turns out that early in the history of the Earth, not only was there a lot more carbon dioxide in the atmosphere, there was a lot of other greenhouse gases that we don't deal with much now. There was methane, which of course we still worry about, but there was ammonia, there was nitrous oxide, there was a lot of other chemicals in the air that we don't have now, and we don't have them because they oxidize. So why didn't they oxidize way back then? Why do we have this wealth of greenhouse gases keeping everything warm? Well, the answer is there wasn't any oxygen. Oxygen reacts with everything. And so any oxygen that was in the Earth's atmosphere early on got absorbed by rocks, by whatever was available. I guess mostly rocks, combined with other elements in the atmosphere, but there was no free oxygen, no O2. So if we look at the relative oxygen, and again the heavy blue line is our current oxygen level, we think at the very beginning there really wasn't much free oxygen. When plants started photosynthesizing, by plants I mean little single-cell, very primitive creatures that were able to photosynthesize, they started producing oxygen. We don't see it rise, though, for a long time, 1 billion years or more. And it's thought that the reason is there was a lot of sinks in the ocean that were just hungry for oxygen. As soon as it started being produced, they went, sucked it all up, right? But eventually they got filled up, and we started getting some oxygen going into the atmosphere. And that's that little uptick after 2 billion years. Well, oxygen's bad for all these greenhouse gases that were keeping the Earth warm, right? So everything froze. Now, whether it froze all the way, froze the entire ocean all the way to the equator is not known, but you can track where the continents were at that time from their magnetic signatures. You know a lot of them were at low latitudes, and they all show signs of glaciation that date back to this period. So it's pretty credible that a very large part, if not all the Earth, was just frozen solid at this point. Now, if you remember the earlier picture of the faint young sun, the sun's getting bright enough about this time to actually start thawing things out anyway. Okay, so eventually that did come to an end. The oxygen level kind of flattened out. Then it has another uptick, and it's less clear how that really triggered the next stage, but actually there are 3 separate ice ages, 2 of which may have been global, that happen around the time the oxygen level starts rising again. Now the reason it's flat in there is that it's being taken up by rocks on land. But eventually it does start rising, and things did thaw out. But there is evidence that we have had many ice ages over time, and actually more than just these. These are the big dramatic ones you can see easily in the geologic record.
So you're suggesting with that graph that there was like 250 million years where the whole Earth was...
And it's really not known how long it lasted. The problem, it turns out, is that geologists know an incredible amount about the last 500 million years because they can look at fossils. No fossils. So they really don't know how long it lasted. I just drew a big fat line so you could see it easily. Yeah, it's a good question. Were these really snowball events? We don't know. They were pretty dramatic, and they appear to have covered a lot of the Earth. That's all we really know. So I think I'm going to leave it there and make room for the next question.
So is it possible that oxygen is poisonous to a lot of bacteria. That the oxygen level off because it was just like right at the toxicity level for these things and they hadn't figured out how to deal with it.
It's a reasonable hypothesis. It's really not known why it leveled off. It's known that there were big sinks that were hungry for oxygen, and that counts for part of it, but that may well have had been a factor.
Yeah, there's a bunch of rocks that are clearly oxidized.
Well,
Right about that.
exactly, and until there starts being free oxygen in the atmosphere, there aren't any red rocks being created. All the red rocks date from that time or later.
Is it possible that some of the small spike variations in the ice age were essentially almost overcorrections as things melt and collapse catastrophically? They're going to really overwhelm the areas, and it's going to take a while for that to adjust and then come to some equilibrium and then probably slip below it to where you have the spikes again.
Yeah, and you can see that very clearly in these meltwater events. It flattens out later. They all have names, it turns out. The younger Dryas and the older Dryas and all of this stuff. These are events where it got cold again. They got cold because of this meltwater and overcorrecting. But the general trend was that it still was warming up. So yeah, this oscillation is everywhere. Anybody else?
Did the carbon dioxide level ever get low enough that plants had a hard time surviving?
As near as I can, it turns out the carbon dioxide measurements for a long time ago were awful. Okay, huge errors. But it appears that the carbon dioxide level in the atmosphere right now is probably about as low as it's ever been. So it was very much higher 50 million years ago when it was a lot hotter, and it's been even higher than that in the distant past. Yeah, so it's slowly being taken out of the atmosphere through these geologic processes and so forth.
Is there any hope for natural corrections for what we're experiencing now with warming or
Oh darn, I wish there was. No, it doesn't look like it. There are some theories that we would be entering the next glacial period if it wasn't for the warming that we're creating, so maybe that's a good thing. The problem actually with all of this, again, is human evolution is linked to these glacial periods. We're cold adapted, and it doesn't take very much more temperature rise before we can't shed our body heat fast enough, which is very bad for us, as you might imagine. So yeah, it looks like the current trend is many times faster than any of these geologic trends, and it doesn't look like the geologic trends can act fast enough to overwhelm